Okay, we are live now. Just wait for some minutes, 3 minutes. So we'll start at 5:05. Let everyone join. Everyone. All right, Anseta, you can start. Just I'll suggest them. Just give me 1 minute. So, guys, today we are going to have a hands-on on our machine learning algorithms, as I said you yesterday. So, this session will be purely on hands-on on machine learning algorithm, and we'll be covering different algorithms that are very important to know if you are learning machine learning algorithm. Anseta, you can start.
Okay, so good evening, everyone. The first algorithm I'd be taking you through is linear regression. Now, what is linear regression? It's one of the most important and one of the most easiest algorithms in machine learning, and it's basically used to find out a relationship between a dependent and independent variable. A lot of you know the way we write functions in math. So it's y is equal to f of x. So whatever value of x you put, like 1, 2, 3, for the function, you get a value for y. So x is a independent variable and y depends on x. Hence, y is a dependent variable. So let's see next. So then now if you have a lot of data points, like you have a lot of coordinates and you plot it on the graph, but they don't have they don't lie on one line. They're all scattered here and there. So then you can have a line that passes in between all of these points. It's somewhere in between. It doesn't pass through each and every point, but it's somewhere between on the graph, and it's the closest to all of those points, and that is why we use linear regression. So as you can see, these are all the data points, and there is a line passing. It's not passing through each and every point, but it's just in between. And if you see, like I already told you, the line doesn't pass through each and every point. So the points are close to the line, and the line now has set of values that we call the predicted value. We've predicted those values, or they're called estimated values. The actual values are still the green color points. So now the difference between the actual value and the predicted value is called error. Okay, so go to the next. So now I'll be taking an example for this. So we have points x and y. Now x is the independent variable and y is the dependent variable. So according to the value of x, we get y. So now there are these 5 points and the plots are being shown. Is everyone able to hear me? Am I audible?
Yes, yes, you are.
Okay. Okay, so I have these set of 5 points. Now, what I will do is I will take the mean of all of these points. Like x, I take the mean of it, y, I take the mean of it, and I find a point somewhere in between both x and y. So I hope everyone can see this red point here in between. That's the mean point. And now this gives us an idea that the line that we're passing through all of the data points will have this one point for sure. Okay, so this one point lies on that predicted line. So now we all know the a line is of the equation y is equal to mx plus c, where m is the slope and c is the intercept. So where it passes on the intercept. Now we have the y value and we have the x value, but we don't know what the slope is. So we don't have a line. We just have one point. So now how to calculate the slope? I'll be taking you through the steps quickly. So quickly and very easily. This is a very easy method. There is a formula. The slope is given by sigma of x minus x square y minus y dash, sorry, x minus x bar y minus y bar, and then divided by sigma of x minus x bar square. So this is the formula. Now how we find out these values and substitute in this formula? So we have x and y. First, I'll be calculating x minus x bar. So x bar is the mean of x values. So the mean of x values is 3. You can see there. So now 3 minus, so now from every x value, I'll be subtracting the mean value, which is 3. So 1 minus 3 is minus 2. Similarly, you get the whole column of values. Now again, I do y minus y bar. So you can again see the mean of y is 3.6 and y minus y bar will give you values like respectively. The whole column is being filled. Now to find sigma of the numerator while finding slope, the numerator side of the values would be given by multiplying the values and then taking an addition of it. So here you can see the last column. So this is like directly the answers are all given. So you do multiplication, you take the addition of everything, and for the denominator it's x minus x bar the whole square. So again the calculation's been done, and when you add everything you get the numerator and denominator. So now with this we have the slope. Okay, so I'll be substituting it in that equation y is equal to mx. Again you can see it on my screen. The substitution has been done, and with this we'll be able to calculate the intercept. So 3.6 is equal to 0.4, which is the slope, into 3, the value of x plus c. From this we get the value of c, which is 2.4. Now we have the slope, we have the intercept, which is what we wanted to calculate. Now x and y are variables and you can put any value for x to find the value of y. Okay, so that's so it's the same thing here. So now here I'll be putting different values of x. I hope you can see, is it visible, the values, or is it small?
No, it's visible.
Okay, so I'll be putting different values for x. So 1, 2, 3, 4, 5, and respectively I'll be getting values for y. So x is independent, y is dependent on x. Now mean square error. This is a very important concept when you are doing linear regression. So you get a line and everything is fine, but the error has to be minimized. You can't have a very big error. You can't have your line passing through anywhere. You know, it has to be very close to all the points, and the error has to be very minimum. So let's see how to do that. Now, what you do for mean square error is I'll be showing you here. So if you can see the points, the predicted line, so the line we got, it obviously has points on it. So we just go perpendicular to it and we see for the actual point. Now we take the difference of the actual and predicted value and we square it, and after squaring you take a sum. And for example, I have 5 points here, I have the errors for 5 points, I square the error, and then I just divide it with the addition of all the points of the number of points, which is 5. So I divide it by 5. Okay, so that gives me the mean square error, and that has to be minimum. It can't be very high. So the best way of doing it is, taking different lines with different slopes and intercepts, and then finding the line that has the least error. So that's how you get the line. Now, the best fit line is again the line that has the least sum of squares error. Okay, so now there are infinite possibilities of slope and intercept, like I told you, and the best line is wherever the sum of squares is least. Error has to be there has to be very less error. There cannot be anything that's errorless. It's just that it has to be very minimal. Now, another important concept, R square. So it shows how well the data is fit into the model. And for R square, it has to be very high. The value of R square has to be high. That signifies a good model. Now, again, this I'll be going very quickly. So you have a line, and you have the y values of it. These are the predicted. So these are values from the line itself. So you have x is going to be independent. So x has 1, 2, 3, 4. So corresponding to the x values, whatever y values are on the line, you take those, and then there is an R square formula given, like how we did previously. Same way we need to do it. This is the working of it. Okay, and now you will be able to see on the slide. So if R square is equal to 0.3, this is the graph. Now if you remember, I told you R square has to be highest, and that's when it becomes a good fit model. So R square is 0.3. It's pretty low. Now if I go R square is equal to 0.7, then you see the points are more closer to the line. Whereas if I do this 0.02, the points are far away from the line. So that's how we understand that 0.7 is a good fit. Okay, R square. So this line is good for these set of points. Now, where is linear regression used? So it's used to evaluate trends and sales estimates, and then price changes, risk of financial and insurance domains. So all of these things, these are a few examples where linear regression is used. So now I hope everyone has understood the theory behind linear regression. So now we'll be heading to our code. So this is a very important code, obviously. We implement that in Python. In this session, I've implemented that in Python. So I'll be sharing the code. Just give me a moment for me. Okay, so I hope you can again see what I'm sharing. And so this is the code. So this is basically the salaries of people. Now, salaries not necessarily have a linear relationship. It's not like, this is basically a relationship between years of experience and the salaries of people. So now again, you can keep in mind that salaries don't have to be like, okay, if a person's worked for 1 year, he'll have this, but 2 years, and it's not a proportional value. Salaries of people depend on the grade, depend on the number of years they've worked. So everything taken into consideration, it doesn't give you a linear relationship. Like not a linear, exactly doesn't give you. It's not proportional. Okay, so that's why we use linear regression to predict what could be the salary of a particular person after n number of years in a particular position. So first of all, I'm importing all of these libraries. So if you can see, import numpy, np, pandas, matplotlib to plot the graph. And then I will be reading this data set from my CSV file, which is salaries.csv. I'll be showing you the CSV file also. So this is my CSV file. It shows you the years and the salary. So years is obviously independent, and salary depends on the number of years in a way. So why? So my salary is y, and number of years is x. This is the CSV file. It's got around 31 values. So this is what we're going to be using. Okay, so I've finished reading my values from our data set. Now I'll be assigning x and y, like I told you, independent variable, dependent variable. Independent is the number of years, and y is my dependent variable. Now, as you know, in machine learning, it's very important to train and test. Okay, so some values are taken, more number of values are taken to train an algorithm to work in a certain way, and testing is done on less number of testing is done on the actual values to get the most efficient result. Okay, now, oh wait, okay, now we will be calling the linear regression. So now we have a library called sklearn that helps in various activities related to machine learning. So now regressor is my object for linear regression. Now I will be using regressor.fit. The first I'll be doing with the train values to get a equation for my train values, that's x and y. And now I'll be getting a line for the so now I'll be predicting the test set results also. So first I'm done with producing a linear equation for the train values, that I'll be using it for the test set results. Now I'll be having two plots. One is for train and one is for test. So you can see here, scatter is going to just give me a plot between x and y train. The color I've chosen is red, and plot is going to give me the line in between. So scatter is going to give me the points that are all scattered here and there, but plot is going to give me the straight line that I need in between all of the points, and that the color is going to be blue. The title I'll be choosing is salary versus experience, and I can also label. So matplotlib gives me the freedom to label the x and y axis, and then finally show. And then again for the test, uh, again for the test points, I'd be using scatter and then plot title, same thing. So I'll be having two graphs with this code. So I'll run the code and I'll show you. Okay, so this works, and this gives me first the training set. You can see how close the line is to the points. It doesn't have a very huge intercept. It's very close. It's right in between all the points as much as it could be. So this is for the training set. Now the actual one, which is the testing set, it appears here. So this also you can see we've got like by the looks of it, it looks right because it's very close to all our points. So, yes, so with that, I'm done telling you about what linear regression is. I hope all of you have an idea now. It will obviously need for the code, especially, it'll obviously need you to practice and do it by yourself, and that's how you will get better at it. Thank you so much.
Thank you, Ansita. Okay, so guys, this was the that we have seen. Okay, so these algorithms we work especially with the continuous values, as I said before. So this was one of the important algorithm in machine learning. Now we will start with the classification algorithms. Okay, so now Shivam will let us know about what is a decision tree and what is logistic regression. And while even logistic regression is called as a regression, but still it's in the classification, he will answer you that question. So let us have a look with that.
So good evening, everyone. Myself Shivam Madalia, and I'm currently a core team member of AML domain at GDSC. So now let's start with the next topic as Fazan said, the classification algorithm. So I'll share my screen. Or is it visible? So first of all, let's see that what is classification. So classification is a type of supervised learning in machine learning where the algorithm learns to categorize data into predefined classes or categories based on a set of labeled training examples. The goal of this classification algorithms is to learn a decision boundary that separates different classes in the data. Now, examples of classification algorithms can be like spam email detection, like where it detects whether the mail is a spam or is it a normal mail which we will send to the inbox. Then is it a sentiment analysis program where the algorithm will learn to classify text as positive, negative, or based on the tone of the text? Or is it a normal image classification algorithm that tells you that whether the image consists a dog or a cat, for example? Maybe it can be an aeroplane and boat. So these are all the applications of classification algorithm. Now let's move towards the next slide. That is why linear regression would not work in all the cases. Like why we should learn classification in the first place. So even though linear regression is a powerful tool for predicting continuous values based on a set of independent variables, however, there are some cases where linear regression may not work as well or may not be appropriate at all. First and foremost, linear regression assumes that there is a linear relationship between the independent and dependent variables. So if there doesn't exist a relationship that is linear, then how will the linear regression model be able to capture those features? So the prediction will not be accurate in such a case. And also, linear regression is not well suited for categorical data such as gender or job titles or things like that, since it assumes that the independent variables are continuous. One solution to this is to use dummy variables to represent categorical data, but this can also lead to overfitting. So we'll see now the first type of classification algorithm, that is logistic regression. So let's look into the definition of it. So logistic regression is a statistical model that is used to analyze the relationship between a binary dependent variable and one or more independent variables. Now, what binary dependent variable means that it's a variable that can take on values such as, oh, okay, it only takes two values, such as yes or no, true, false, or maybe presence of something or absence of something. So it's just a binary dependent variable. The goal of logistic regression is to estimate the probability of the dependent variable taking on a certain value based on the values of the independent variables. Now let's look into the main features of logistic regressions. So first feature is the binary outcome. In this, it's the main feature of logistic regression. The outcome or dependent variable in logistic regression is binary, meaning it can only take two possible values, such as yes, no, as a pass fail, as I said earlier. Now another thing is the sigmoid function. Now this is very important part of logistic regression. Like this is the only thing that differs or differentiates the linear regression and logistic regression from each other. So sigmoid function is a mathematical function that maps any real valued input to a value between 0 and 1. It is used in logistic regression to estimate the probability of a binary outcome. The sigmoid function is an S-shaped curve. You can see the graph that I'll show you. So this we can see that this is an S-shaped curve, sigmoid x. So it is basically going to apply the sigmoid function to the answer or to the function, or to, we can say, to the result of the previous equation that was given by Ansita in linear regression. So y equals to mx plus c. The output is then passed on to the sigmoid function, and then we plot it to the graph. So it's basically two-step process in logic regression. Then next feature is linear relationship between predictors and log odds. What this mean is that there is a linear relationship between the independent variables and the logarithm of the odds of the outcome. Now this relationship is modeled using the sigmoid function. So that is how it takes place. And last, the foremost feature we can say is absence of multicollinearity. This must be a condition, otherwise our model won't be working properly. So what it means that it will assume that there is no multicollinearity among the independent variables. Multicollinearity occurs when two or more independent variables are highly correlated with each other, which can make it difficult to estimate the effect of each variable on the other. So you must make sure that the two variables or the two independent variables are not highly related with each other. Now, as Faizan stated a question like why logistic regression is a classification algorithm, though its name has regression in it, this is a very interesting question. So, but as we have learned, So I'll give you the answer for that. The logistic regression model is trained on a labeled dataset where the labels represent the classes that we want to predict. The model learns the relationship between the input features and the probability of belonging to each class. The model uses a logistic function, which we learned earlier, that is the sigmoid function, to convert the input features into a probability score. Now, this probability score is then it probability is always between 0 to 1. We know that. So the logistic function will map our continuous variable to between the 0 and 1, which can be interpreted as a probability. Therefore, logistic regression is a classification algorithm because it learns to predict the probability of an input example belonging to a particular class rather than predicting a continuous output variable as a linear regression does. So now let's see the coding part of the logistic regression. So this is the implementation of the logistic regression. I have done it in a notebook. So the example or the dataset that I have chosen is the customer churn dataset, which Fazan showed yesterday. But he solved the problem by using neural nets. So we are going to see the another approach for that, that is the logistic regression. So let's actually first see the dataset how it goes. Yeah, so dataset looks like this. It has, I would say, many columns are there, so there are many features you can see, but every feature is numerical. We can see earlier it wasn't because this is a pre-processed data. It means that the data has already been cleaned. So we are seeing only numerical values here. And it has some features such as tenure, age, address, income, education, employee, equip, call card, and things like that. So of course, we are not going to take all the features into the consideration. So first, let's start by importing the libraries. That is pandas for data manipulation of the data frame, then numpy for array processing, and I've also imported sklearn pre-processing module, which will let us do some pre-processing for in our data set. And matplotlib is for the data visualization. Then we'll load the data through the pandas function read underscore csv. Now, since we have read the data, we can also see the data by using the head function, which returns us the first 5 rows of the data set. And by using the dot shape function or attribute, we can see that the shape of our data frame is 200, 28. It means that there are 200 rows or instances in our dataset and 28 features. Now, from these 28 features, one is our target feature, which you can see here. The last one, the churn, that is our target feature, and the rest 27 are the independent features. And by using the dot info function, we can have the basic information such as about what are the data types used in our dataset. So we can see that almost all of them are float. So as I said, it is a pre-processed dataset. So they have pre-processes in a way that all the data types are float. So now we are going to take our input variables or the features that we are going to select for our logistic regression. So we have only selected this much for our, so we have filtered our data set to only this much features. And then we have converted the type, that is the data type of churn, that is our target variable, to integer. So we don't want it to be float, we only want it to be integer, that is 0 or 1. Then again, we can see our data set by using the head function. Now it has only those columns that we have mentioned, that is tenure, age, address, income, education, employee, equip, call card, and wireless. These are all the input features, and the output feature or the output label is churn. So we have converted into integer. Now again, we can see the shape. Of course, the rows won't be changing. 200 remains the same, but the features have been scaled down from 28 to 10. Now we are going to convert these features into an array by using the dot as array function from the numpy module. Once we convert that, we are going to transfer it to the new variable x. And then similarly for y, we are going to convert the churn column to an array and then store it in the y variable. Now, as I said, we will be doing some pre-processing on the data set. So we can see that in the data, some columns have values that are above 100, that is 136. But on the other hand, this education and employee, these numbers are very low, 5, 2. So our model will be biasing those numbers. So we don't want that. We want that our model should learn the general features rather than just relying on the number, the numerical value. So we want that to scale down to a proper scale. So what we'll do that by applying this standard scalar function, we scale our data distribution to a standard deviation of 1 and a mean of 0. So we can see that all the numbers now are in a particular range. It has the numbers have been updated. Now we can apply the train test dataset split by using the inbuilt function present in the sklearn library. And what I've done is I have done test size as 2. It means that there will be a 80-20 split as Fazal has taught us yesterday, the train test split. And a random set of 4 that will return me those same train and test split every time I run this cell. Now we can see that it has been splitted. The train test now has 160 rows and the test set has 40 rows. Now this has been distributed randomly, so you don't have to worry about that. It handles it internally. Now we are going to make a model. So for that we will import the logistic regressions class from the sklearn module. And we are also importing a matrix, evaluation matrix, that is the confusion matrix, which we'll see at the last. So once we create the object of logistic regression, we are going to fit our model, that is the X train and Y train. Now what you are seeing here in the bracket, those are hyperparameters. Now C equals to 0.01. Now C is actually the regularization term for our model to learn things slowly. And solver is a like optimizer used in logistic regression. So the solver I have taken is linear. Now this solver is generally used when we have a data set of small size. We can also use different solvers, which I have done in the last two. I'll show you that in the last. For now, we have used the linear solver and the C's value is 0.01. By taking the smaller value of 0.01, we make sure that our model doesn't overfit the data. Since the data set is small, it might be bound for overfitting. So the smaller value of the smaller value of C, we make sure that it doesn't happen. Then we'll run some predictions on our test data, and we see the input, the output is present in the form of 0 and 1s only. But as I mentioned earlier, that the logistic regression, this thing algorithm returns the probability of the classes. So we can also actually see the probability of this test, which is written here 0.54 and 0.45. So it means that the probability of this input set, that was the first input set, is it is 0.54 probably sure that it is going to be a zero output label. So that's how it works like in logistic regression. And while evaluation, we have got evaluation matrices such as precision score and recall score. Now these two are the most important evaluation matrices for classification algorithms. Apart from this, we also have F1 score and confusion matrix. So first of all, let's see what is the precision that we are getting. So the precision that our model is giving is 0.72, and the recall that our model is giving 96, 0.96. So I would say it's the pretty much good model for recall matrix. And precision, I think we need some more hyperparameter tuning or maybe more data to get a higher precision number. Then we are going to see the confusion matrix, as I said, and we'll also import the classification report. This function is also very useful to evaluate our model. Now, this is a function that actually plots our confusion matrix. So let's see the plot. By calling this function here, we are now seeing the plot of the confusion matrix and the test that we have run. So confusion matrix usually consists of 4 sections, that is true positive, true negative, false positive, and false negative. So true positive means that the model predicted the label to be 0, and in actual also the actual answer for that was also 0. So we can say that our model has performed correctly in the true positive portion. And for the true negative portion, our predicted label was 4, that is 1, and actual answer was also 1. So it matches completely. So true negative and true positive are the parameters that checks whether our model is classifying the input correctly or not. On the other hand, false positive and false negative means that, let's say that this predicted level, we predicted the churn to be 0, but in actual it was 1. So this was a wrong part of our model. And again, on the other hand, if the model predicts the churn to be 1, but in actual it was 0. So that this means that our model has misclassified the input features here. And classification report, once we run that, we see a report which gives us the precision recall F1 score of particularly all the output levels, that is 0, 1. For 0, the precision was 0.73 and recall was 0.96. And 1 is 0.86 and 0.44. This means that our model is 86% sure when it's going to classify a person who is going to churn. And on the other hand, 0.73, it is sure when the person is not going to churn the company. And lastly, we have got the log loss matrix. This measures the loss that is given when we are doing the training. So this is desired to be a lower value. So log loss, we don't have to calculate it manually. Of course, we have library for that also, sklearn.metrics, import log loss. And then, but what we have to pass here is we have to pass the y test. And the second parameter that we have to pass is the probabilities. Probabilities, as I've displayed earlier, these are the probabilities that our model predicted. And based on that, it will calculate the log loss, which comes out to be 0.60. And lastly, as I said, that there are different types of solvers that are present for our hyperparameter tuning, and one such solver is SAG. So I've again trained the data and I've run the test, and log loss this time was 0.61. So the loss has been, you can say, increased when I use the solver as SAG. So as I said earlier, the lib linear solver is used when the dataset size is small. So I think that's how we can conclude that log linear is doing a fine job of classifying our data. Now let's move towards the next algorithm. So yeah, decision tree classifier. Now let's look into the definition of the decision tree classifier. So a decision tree classifier is a type of ML algorithm used for classification tasks that involves constructing a tree-like model of decisions and their possible consequences. In other words, it is a tree-like structure that models decisions and their possible outcomes based on input variables. Now, it is a part of a supervised learning algorithm, which means that it learns from the labeled data, where each input variable is associated with a known output or class. Now, decision tree classifiers have several advantages, including their ability to handle both the categorical data as well as the numerical data, their interpretability, and their ability to also handle the missing values in the dataset. Now, the decision tree classifiers are widely used in many applications such as data mining, pattern recognition, and decision making in business and industry. So the example, first of all, let's try to understand this with an example or the diagram. So in the diagram, we can see that this is a decision node, this is a root node, and based on some condition, we are going to split the data into two categories. We can see that there are two branches of it, decision node and decision node. We can see here. So it's decision trees. You can take it like it's a very large if and else ladder. It's nothing rocket science or thing like that. It's just going to categorize the data based on some condition. For example, let's say that we want to classify some people's salary, right? If it is above 50,000 per month, then we are going to take this branch, the left subtree. Or if it is not, then we are going to take the right subtree. So basically, it works like that. And in the end, the leaf nodes are there. So those are our outcomes, or we can say the outcome categories or outcome labels of the target variable. So now let's see the main features of decision tree. The first and very important feature is the splitting criteria. Decision trees use splitting criteria to determine how to divide the data into branches at each node. The common splitting criteria includes the Gini impurity and the information gauge, which measures the degree of impurity or uncertainty in the data. So the splitting criteria also we have got two options in that, the Gini approach or the entropy approach. So these both are some mathematical methods to select the best feature for our decision making. Then the next feature is pruning. Decision trees can be pruned to overfitting, where they fit the training data too closely and perform poorly on the new data. To prevent overfitting, pruning is often used to simplify the tree by removing branches that do not improve performance on the test data. So this is basically done to remove the overfitting of the model. Then interpretability. Decision trees are interpretable, meaning that the decisions made by the model can be easily understood and visualized. This makes them useful for explaining the reasoning behind the model's predictions. What it means that we can actually plot the decision tree using some Python's function like and also some libraries that Graphis. And lastly, we have got non-linear relationships. This means that decision trees can capture non-linear relationships between input variables and the output, making them a flexible and powerful model. Now, in linear regression, we learned that it is not able to learn the non-linear relationships. The decision trees can handle that, so that is the advantage of the decision tree. Now, let's dive into the implementation of decision tree. So, okay, first, before that, we will see the data set that I have taken. Now, in this data set, there are 17 columns, and this time it's a large data set. I would say it has 11,000 rows. So, it has a large data to learn, and that's a great thing. So this is the data set. It contains the age, job, marital status, education status, default, like whether he has a default loan, something like that, balance in his current balance in his bank, and housing, whether he has applied for a housing loan earlier or not, and loan whether he has a current loan, then the way of his contact, and many other features are there. And but the main thing is the target variable, that whether he is going to deposit into the bank or not. So that is what we are going to predict in this model, whether the candidate is going to deposit a loan or not a loan, but a deposit, a fixed deposit in a bank or not, based on the features that age, job, marital, education, based on these features. So now let's look into the code. So we can see that I've imported many things here, but you don't have to worry about that much. The pandas and numpy are a must for machine learning algorithm. Then you can see that I've taken the decision tree classifier, which will be the main class for our model that I've imported from sklearn.tree. Then I've got train test plate and some evolution matrices like accuracy score, precision score, recall score, F1 score, then area under the curve, and of course the confusion matrix. And then I've also imported the standard scalar function for pre-processing. And for visualizations, we are going to use matplotlib as well as Seaborn, which is a data visualization library in Python. Then we are going to read the data, and then you can see the shape is that it has 11,000 rows approximately and 17 columns, from which one column is the deposit, that is the target variable, and others are the features of it. By running the bank.info cell, we see that the data type is just of two types, that is numerical data, and the object means it's a categorical. So we will need to convert it to numerical data by doing some pre-processing. Then by using the bank.describe, we see the standard deviation and mean of the numerical columns or features. We can see that the mean age in our data set is 41 and mean balance of all the candidates that we have data of, that is 1,500. And then we'll check that if we have got any missing values in our data set. So by running this cell, we can see that it returns false. It means that there is no missing value. So that's a great sign that we can move forward. Now we are going to see some data visualizations for gaining insights. Now the code may seem a bit complex, but the main lines that are going to plot for us is this line. It's going to plot a pie chart for us by doing this pie function. We actually plot a pie chart, and others are just the parameters that we can play with, and those are colors and things like that, maybe labels. And then we are also going to plot a bar plot. Okay, that the bar plot signifies the education, balance, and whether the candidate is depositing or not in the bank. So we can see that the candidates with the education of secondary level are actually higher in number in proportion to those who have tertiary, primary, or unknown education. So we can see that secondary, the people with secondary education have less number of deposit compared to low. But on the other hand, in tertiary, we can see that the deposits are higher than the persons who have not deposited. And from this pie chart, we see that the number of candidates who have deposited and along with the number of persons who have not deposited. So I would say that this data set is good for training as it is symmetrically skewed. So we don't have to worry about any bias in this data set. Moving towards the next plot, these are the histograms for all the numerical values. We can see that our age is concentrated towards the 30s and till the 30s and 40s. So we can see that most of the candidates that have attended this marketing campaign are from the age 30 to 40, and the balance of the people with the frequency of above 8,000 is around zero. But we can see as we move towards the right side, the frequency is getting decreased. And similarly for the other graphs. Now we will see another graph that actually shows the relation between the job and the balance. By this, we see that the person who are retired generally tend to have more average high balance in their account, and we can see that the people working in services are having compared to other job titles, there is a lower average balance in their account. Now, as I said, we need to convert the categorical values to the numerical values. So we are going to need some data pre-processing. So as Fazan showed us yesterday that we are going to use the get dummies function from pandas that will let us convert the categorical values into numerical values by adding some special columns to our dataset and removing the existing columns. But for that, we need to convert the columns first of all into the string data type as it was object earlier. So this function doesn't run directly on the object data type. So we need to convert it to string. So I have converted it manually and then I've passed it to get the this function. So we got the what we can say the pre-processed columns and I've stored in it the bank data set. And then I'm applying the standard scalar pre-processing to the numerical data to scale it down to a we can say a common scale. And then I'm fitting and transforming it. And in the end, we get the data set that is completely pre-processed. You can see that standard deviation is 1 for the numerical values and the mean of the numerical values has been scaled down to 0. Now we can see the updated data set. The numerical values have been changed and the other columns have been added by the getDemis function. So we can see that the columns have increased to 52, which is quite a large. And of course, the rows are 5 because I've used the head function. But of course, the rows are 11,000 behind the scene, we know that. And we're going to split the data now. So we are going to drop the target variable that is deposit. And we are also dropping this durations column. Now, why we are dropping this duration column? Because this is highly, we can say, correlative to the target variable. And this will increase the biasness towards this variable in our model. So we have to remove this function. And first of all, the reason why we are doing this logistic regression model is that we want to predict that which customer should we give called. Now, if you are going to provide the duration data in the trading itself, then how will the model learn at which customer is going to be a potential deposit to the bank? So we are going to need to remove this column so that the model will run the general features rather than just learning from this duration feature. And the target variable is the deposit. Then we are going to apply the trend test split. Again, it's an 80-20 split with a random set of 42. Then we are going to instantiate the model. The decision tree classifier class was already imported. So now we are going to make an object of it with some hyperparameters such as criterion is entropy. As I said during the theoretical part of the decision tree, there are two types of criteria to actually learn the model. First is entropy and other is Gini. So you can try both of them and whichever outputs is good, you can select that. So I have taken the criteria as entropy and the class weight is selected to balanced. Why have I done this? Because if the data set is imbalanced, this feature, this hyperparameter will give the higher priority to the minority data and lower priority to the majority data. So it is going to balance our weights, the parameters. And max features has been set to 3. Then we are going to fit the model and get some predictions on it. And after getting the predictions, we see the evaluation metrics. The accuracy is coming out to be 64, precision is 62.5, recall is 63, and F1 score is 62, and area under curve is 64. Now, the main thing is the confusion matrix. Now, we see that the true positive of our evaluation comes out to be 673, and true negative is coming out to be 763. And true false positive is coming out as 403 and false negative is coming out as 384. So we can see that the true positive and true negative are relatively higher than both of the false positive and false negative. So we can say that model is working in a quite good way. So yeah, that's all about the implementation of decision tree. So I'll just show you some applications of these both algorithms. That is in medical research. We usually use them in medical research for like classifying whether a patient has a diabetes or not. Maybe we can also use to predict whether patient has some cancer cells or not. For marketing, we also use it for classifying some customers, like whether he will be a potential buyer or not. Then, of course, in fraud detection, usually the finance team in the companies run some fraud detection algorithms to detect the frauds in their financial statements. Then credit scoring, political science, and there are many applications of the both of these algorithms. So these were some main applications. And yeah, this concludes the decision tree and logistic regression. Thank you.
All right, thank you, Shiva, for the great presentation. And now we have knowledge about what is decision tree and logistic regression in a better way. Now I will start with the support vector machine, guys. I hope my screen is visible to all.
Yeah,
Okay.
actually, I can't hear you.
Hello, am I audible now?
Yeah, you were muted, I think.
Okay, okay, okay. So, okay, so I'll just restart again. Yeah, so I was talking about so I was talking about the support vector machine. Okay, so support vector machine is a machine learning algorithm that helps in classification of data points. All right, discrete data points. So let me give you a scenario first. Like this is a scenario where we can say that this is a data set of patients which are on a high risk of developing a cancer. Okay, so we have features such as clump, uniform size, uniform shape, and then you have something called features, different features, epic size, bare nuke, bland. These are the terms that are used as a parameter for a cell, okay, to determine a cell. And this is a class. This is a class where you can see this is a numerical value. So this is already pre-processed into a terms of a numerical value instead of categorical. So two stands for benign. Now these benign cells are non-cancerous cell, you can say, that does not spread. Whereas this class 4 belongs to malignant cells. Okay. So these cells are cancerous cells that actually spread across the human body and causes issues. So these are our features and class is our target output. Okay, so let us understand now what exactly is support vector machine. Okay, so support vector machine is a supervised learning. All right, so supervised learning algorithm that is used for classification and regression analysis. So SVMs are based on idea of finding a hyperplane in a high dimensional space. that maximally separates the data points of different classes. Now, what do I mean by this? Is you can see from the graph itself, if we plot the classes in a graph, okay, if we overlap these two graphs together, we are having blue as malignant and yellow as benign. All right, but if you see, we don't have a proper classification, right? We don't have a proper classification or any separatable line. So see, we can make a separatable line by understanding, but what about the algorithms, or what about the computers that we use? Like, so they have to be they have to make some decision separating line. So if we see this is like we cannot have a decision separating line. So what we can do, what a solution for this could be, we can take it into a higher dimensional. For example, that we are having a one more dimension like this. So what happens? This is what happens. Now these are separated. This is my malignant cells, and these are my benign cells. And in between now we have the hyperplane. Yes, you can also just imagine by keeping your two hands over one another, right? And if you see they are they are merging together, right? So if you want to separate them and I want to find some hyperplane or some separating line, just you just pick off your one hand on the upper side, so you will find automatically that okay, now those two hands are separated, now fingers, okay. So this is the basic idea now of the support vector machine, how it performs the classification. And support vector machine is one of the most used algorithm, okay, in real life also, just because if you see the data, this is like mixed data type, right? You don't have any proper separatable line, and in real life also data are like this only. Data are not very linear, or data are not very uniform. They are very like they're very varied, like, okay. So let us understand how a support vector machine works. So first of all, as I said it, like it's mapped the data into a higher dimensional. All right, just like this. This is the higher dimensional, and then it finds a separator. This is the separator, right? This is the separator. So now the question arises. Two challenging question arises. So first question is, how do we transfer data in such a way that a separator could be drawn as a hyperplane? And second question is, how we can find the best optimized hyperplane. All right. So let us answer these questions one by one. Okay. So how do we transfer data in such a way that a separator could be drawn as a hyperplane? Okay. So as I said in before example, we were working with 2D, okay, two dimensional, and then we moved into three dimensional. All right. But let us take a lesser dimensional example. If I'm taking a one dimensional example, that we have only one feature here, okay, just to simplify things so that you understand better. So this is one dimension. Now tell me, how can we classify? Like, you cannot classify. This is in one horizontal line. See, this is the blue, this is red points, these are the blue point. So this is not linearly separable, right? So what we can do, we can increase the dimension from 1D to 2D. So here we can see the function is now x square. From x, it has been increased from to the x square, right? So if the functions is been increasing the dimensions, now we can see you've got a graph with the U shape, and this is our hyperplane that we can separate through. So I guess, so this was just to give you an example that from one dimension to another dimension how things work, okay. Usually we work from two dimensional to three dimensional, but here we are working, just for an example I've showed you, from one dimensional to the two dimensional. And now splitting this up into different dimensions is called as kerneling. Just remember, this term is very important in SVM. This is called kerneling. Kerneling means changing your data, like plotting your data points from one dimension into another dimension or bigger dimension. All right. So we have different type of kerneling method. There's linear, polynomial, radial based functions, or sigmoid. So like these functions, they are pros and cons into themselves. So you don't have any special method to, we can say that okay, this is the better kernel function. You have to plot them all. You have to, try and error. As I said yesterday, that machine learning is all about try and error. So you have to try and error and see which fits best for your data. All right. Now, second question that we were, so one question has answered, like how we transfer data. Like, so we transfer data. This answer is by using kerneling. Okay, so this is kerneling method that we increase the dimension space. Now, second question was that how can we find optimized hyperplane, right? So this optimized hyperplane is something that needs to be, in between the data points, right? So for example, we have two data points here. This is the blue and this is some orange data points here. So now if I want to, I have to find an optimized hyperplane. So it needs to be have a maximum distance between these two. what is the what is the major goal of the hyperplane is to have maximum distance. The more the distance, the more it is separated, the more properly it is separated between 2 points, right? And these are vectors. These are support vectors, we say. These are support vectors. And just imagine, like, only we require these points to understand the separability between 2 points. Okay, we don't require these all points, because see, we don't have to work with them, because they are not a point where we are actually separating another class. So right, these are two classes. So we need to work only with those points that are required, or that are used to separate two classes. So we have one, two, three. These are the three support vectors. And these there's a line of equation, like you can say, for the hyperplane, that is due to raised to t transpose x plus b is equal to 0. So this is the line of the equation. And whenever you plot, when you give value for the w or the b, okay, the terms, okay. So in the terms you will get a result. If it is lesser than 1, or its negative value, then we could say that, okay, this falls into this category. Or if the answer is greater than 1, or it's nearly to 1, then we can say this lies in this category. All right, so this is category A or category B, we could say. So depending upon the values that you get from the equation of the hyperplane, we could say that this belongs to group A or group B. All right, so we've answered these both two questions: how to find the optimized and how to transform the data. And now let us see some applications of support vector machine. Like, this is using image recognition, text categorical assignments. Work with the data that needs to be separate, okay, especially classified, detecting spam or ham. All right, sentiment analysis, cancer detection, like we are using right now, and detection problems, especially the detection problems. And support vector machine is the most widely used classification algorithm. All right, so let us understand the coding part now. All right, so the most important part is how it's being coded, right? So let us understand it. So here, like, this is just a general importing the libraries. The first always step in when you write a code is import the libraries. This is like importing pandas as PD used to work with dataset and manipulate dataset, right? NumPy is to work with numerical computations in Python. Matplotlib, this is the sub library, okay. Matplotlib.pyplot is sub library of Matplotlib, okay. Okay, this is a sub-library of Matplotlib, and we alias it as a PLT. Now, what is this as means? This is just to give it a shorter name, or call it instead of writing this full name. All right. So from SQL and model selections, we are importing the train test split as we always require in a machine learning algorithm. And this is a Matplotlib inline. This is actually used when you want to render your graph in your own cell instead of getting into another page and showing it. So this helps in rendering in the same cell, in one cell only. All right, so first we are reading the data set. All right, so this is my data set. This is an encoding, UTF character encoding, you would say. See, sometimes what happens, your data is not in a proper character encoded, right? So you need to encode it in a proper format. Not always, but if sometimes, if you plot your data, and if you're facing error with the representation of your data into a data frame, then you can use this. This is very important. Encoding ISO 88591. This is some code that encodes your data into a proper this thing format. So we have taken it into a data frame. Now we have our data set. Now let us see what is the data set says. ID, clump, as I said before, uniform size, uniform shape, different features that are required, or different sizes, or required when we different parameters, especially in a set. Okay, and this is our class. This is already converted into a numerical value, as we are already working with numerical value. So we have kept our class also in numerical value. Now, let us look at the distribution of the classes based on clump thickness and uniformity of the set. So these are the two parameters that we will be working. That is the clump thickness, okay, clump thickness, and the uniform size. So, like, these are some important features, you would say, because we are taking into consideration for determining a class, whether it is benign or malign. You can take different classes into consideration, but just for now, to plot between two, and to show you how you create a hyperplane between these two data points, we will be taking into consideration. And then if we see the distribution, so I'll explain you the code here. See, this is just a variable axis. Okay, axis is equal to. So what we are saying is that, first of all, if we want the data, we want the class data frame. We are saying that we want four. What this four stands for? As I said, four stands for malignant, right? Malignant data cells. So we are saying that we want to plot the from class. We want to plot the class that is equal to 4, and we want to how many records we want? We want 50 records to plot. All right, these points are 50 points, you would say. All right. So n dot plot is a function that you is used to plot. Okay. So what type of plot is this? It is called a scatter plot. You need to define what type of plot you are actually. This is one of the parameters of plot. Okay, you can explore. There's a lot of parameters always in a function. So these parameters would be only understood when you understand the functions itself, and you research on them how many parameters it can take. X is the clump thickness, y is the uniform thickness, and color is dark blue. All right, so these dark blue points are malignant, and we'll label them as malignant. Okay, then again we have a separator in between them, that is this colon, and then we start with a different that we are asking now that we want to plot class of 2, the class numerical class of 2, that is now benign cells. Here it should be same as that of the malignant cells. And then similarly we are plotting, we are using a plotting method, and we are plotting kind is equal to scatter, x is equal to clump, y is our uniform size, and we are putting it into yellow color. Label is equal to benign. Now this is important, like I said you why we are using that axis. So what will this help us see? If I just run this without mentioning this, so this will be showing it into a different axis. See, we have got different axis, but we don't want like this, right? This is already some classified thing, so we don't want this. So what we want is we wanted the proper merge data. This is how if we run, we'll get a merge data. All right. So now after this, we are checking. Just this is some data pre-processing steps. Okay. So just checking if data types is integer or not. So we found that okay, we are working in all integer, and this is an object. So this shouldn't be an object. Okay, because if you can see this is a numerical value, but still this is object. This type is object. All right, so we need to convert it into a integer. So for that we use some pre-processing steps where we define a new data frame, and then we use a two numeric method to convert the object values to numerical values. This error is used when we want to we want to convert the numerical value exactly. And if there is some categorical value, we have to put nan over there, like not a number. Okay, and then what we are saying that from when we are done with this, with when we have converted it into a numerical value, now the not null value will not take the null values, that is nan values. So at the end of this, all of this pre-processing, what we will have a integer data type converted. All right, and then data values will be purely numerical and not an object type. And then similarly we have taken a feature data set, we have taken these data set into consideration to train our machine. All right, and we have converted into an array. All right, and this is how array looks. So this is our training feature data set, and this is our is the target variable that we want. So it's similarly we have converted into an array, and we have passed it into a y variable. So this is x and y. Now we have x and y. So we similarly, as we do in all machine learning algorithms, we divide it in test and train and test and split. We get the test size as 20. We have set the test size as 20, and 80 size as the training. And then we are printing just the training set and the testing set. So in, as I said you, now this is the important step comes. This is the previous step that we already seen in many algorithms. Now this important step which differs SVM from different algorithms is kernelling. So this is how we use the kernelling. As I said, kernelling is used to bring a data from one dimensional to a higher dimensional. And so you can see from here sklearn we are importing SVM, and then we are creating a classifier for it. And in that SVM we are having a parameter that is kernel is equal to RBF. So we are using the radial basis function. You can use any one which fits good for your data. And then you have to fit the model. Fit means train the model. And then once your model is trained, we have to check the predictions, what it has predicted by passing x test values, right? So this is what it has predicted. These are the predicted values, and these are our actual values. See, this is the predicted value, and this is the actual values. All right, this is into array forms. So let us see some accuracy of training model. I mean, this is a training accuracy dot sklearn we have imported. So we could get a training accuracy as 0.97, which is really good. I mean, and this is the score that we are getting from the accuracy of the test. Score is after training. This is the testing score, and this score is for the training score. All right, so this is 97, 96%, and this is the F1 score, that is the whole average score of the model, and this is coming out to be a 96%. So this is like a best fit model, I would say. So, guys, this is how a SVM works. The main part in the SVM is modeling and kerneling, that you would say, and this is how you actually define your kernel into your code. Okay, so I hope you guys have understood the support vector machine, and now yeah. And now Akash Raj will help you guys by knowing the clustering, how clustering works. So, guys, how much ever algorithms that we have done till now is supervised learning. This is based on supervised. Now, how unsupervised learning works will be showed by Akash Raj Patel. So, Akash, you can go with it.
Thank you very much. Sadam, I'll be sharing my.
You're welcome. Akash, your mic has been muted.
Actually, yeah, my option to share screen is actually blacked out. I can't actually click on it.
Okay, okay. You just try it once, if it's possible.
I can't actually. My it's black. It's grayed out. I can't actually click on it. The share screen. I think.
So, okay, so you cannot see you cannot see the live screen. You're saying, right?
Yeah, I cannot. I can see the bottom bar. I cannot click on the share screen button because
All
I think
right.
you are sharing right now.
Yeah, yeah. Okay, okay. I'll just stop sharing. Okay, you can see now if the share button is open for you.
Yeah, yeah. Okay.
Yeah. All right. All right.
Okay. Good evening, everyone. My name is Akash Raj Patel. I hope everyone can hear me. And today I'll be covering the K-means clustering algorithm. So yeah, as Fazan said, all of the things that we have covered up until now has been about supervised learning models and what supervised and the difference between what we are learning right now as in an unsupervised learning algorithm versus supervised learning algorithm is basically that a supervised learning algorithm has a labeled data with it. You've seen Kazan and I'm sure other people. You have noticed that when they were showing you the data, they did the 80-20 split. They showed you that this is the data, this is unlabeled data, and we're training our machines on that unlabeled data, and then we're going to check its accuracy on our labeled data to see how good our models were to find to predict the true value of any unlabeled data. In Keynes algorithm and any unsupervised learning algorithm, we don't do that. We use it in a specific case scenario when we have a lot of huge random data and we don't have any labels for them. It could be customer segmentation, it could be large social media analysis, or even image segmentation. It is a need where you have the data and you're asked to classify it. You need to break down the data into separate different clusters, but you can't see any pictures. You can't, as a human, you can't see any patterns. This is where we use algorithms such as K-means. It learns by itself. It tries to do the whole division of data, the whole classification of data by itself without actually needing any label data set. So say you have this data set with you, it's pretty scattered. It's really simplified, so you can probably see that this here is one cluster, this here is one cluster, and this one here is a third cluster. But as a machine, how would you imagine a machine would do this? Once you apply k-means, it does this, but how? That's what I'm going to explain in a few minutes. Yeah. So working of a K-means algorithm. For this, I found a really cool video about this, which does explain it. So say you have, say you start with this random data set, and you give a key, you select three random points and you pass in a k value of 3. K value could be anything. K value basically means how many clusters do you want the algorithm to find for you. So it could be 1, it could be 2, it could be n value. The lower it is, the more broad range of a classification it will try to do. And the higher k is, the narrow it will try to make each cluster. So it really does depend on your use case. So say I selected 3 for this. It will make 3 points on this graph. These 3 points could be anywhere on the graph. This is completely right. What it will do after that is it will try to find the closest points, closest point from each of these points. Let's call these points centroids. So it will try to find the closest points for each centroid. So let's see. It will be something like that. So from this centroid, centroid A, the closest point. What is the closest point? Closest point is basically the shortest Euclidean distance it could find from this centroid point to this point. So this and this have a distance that is smaller than this and this point. So this one was colored red and this one was not. This one is closer to this green point, so it was colored green as well. We do this until we have colored every point on the graph. Okay. So after we do this, we do the second step. What we do is we recalculate the position of the centroid that we have based on the center of the new points that we have selected. So here the x point that we started with is not exactly at the center of all of these red points. So let's fix that. The algorithm will then move this x point and all of the points within to a point to the center, so that now these points are at the center of all of the green colored points that they were originally there. This was the third step. Our fourth step is basically to repeat these two steps again. So as you can see, once we moved them, they were at a new place. So at this new position, this x point, we will now again find the closest points, closest by the shortest Euclidean distance of this red x point with the other points on the graph. So if we do that again, we will find that these two red points are no longer close enough to this x point. They are more closer to this blue arrow than they are to the red arrow. So we would make them blue instead of red. Same thing happened here with green. So we basically did the second step again. Now we are going to do the third step again. We are going to recalculate the position of the centroid, meaning this x, this red x, this blue x, and this green x again. If we do that again, we will try, if we find the center point of new center value of these points again, it will be somewhere like here. After they have moved again, we will again do the point of finding the closest points to these red points. So if we do that again, now we see that these blue points, these points that are initially red are more closer to blue now, and these points that were initially green are more closer to red now. We will continue this until one of two things happen. When we are declaring a K model, K means model, as I will show in a later part of this presentation, we can set a maximum iteration point. After that many iterations, the model will automatically stop classifying and it will just give you a result. This is useful because K-means algorithms are again unsupervised, so they don't actually have a stopping point unless you define a higher ceiling that you should stop there, unless otherwise it will go on for infinity. They don't for most part, because as you will see, when these points reach into the center of these clusters, they will stop moving. They will stop moving because of the point that they are no longer moving. Uh, they are no longer finding any more red points or any more blue points that they can rearrange their center position to. So this will eventually happen, and when it does happen, the model will stop. It will stop in two conditions. Either it reaches a high ceiling where it can no longer generate, it reaches a high ceiling of iterations that we have described, or it can no longer, or in with each iteration, the number of points, the position of the centroid does not change. When that happens, the model is satisfied that it has probably found some clusters in the data. So I hope it was somewhat, you were able to somewhat understand how the math behind it works. It is really simple, and I try to show it in a really small data set. What are the examples of games? Again, in a real world scenario, it is used for customer segmentation, image segmentation, anomaly detection, recommendation systems, and social network analysis. Basically, you can imagine at any point in any place where you have a lot of data, there is a lot of randomness to the data, or at least clusters, and you can't basically paint out the whole picture of what it is. You don't have a labeled data, basically. If it is unlabeled, you should try using k-means for it first. So how do you actually apply k-means method or an unsupervised learning model to anything? That's what I'm going to show you next. So I hope you can see I have created a Google Collab file for this that I will share with everyone. So again, I won't take too much time. A lot of my friends, as you have seen, has already explained this stuff. You import libraries, matplotlib, Seaborn, and Scanmethod. For this, the only thing I have done differently as from my peers is that I have created a dummy data set. You can easily create dummy data set using SQL's database and make blocks. This is a really useful technique that everyone should learn better in data science or machine learning models, because not every time you will find a data, and sometimes creating a data is just really fast and intuitive other than finding a data, cleaning it, and then applying a model to it. It just gives you a head start. So in this data that I have created, it has 300 samples. It has four centers, and the average standard deviation from each point from the center is 0.6, and it has a random state of 0. If you put random state non-zero, 1, 2, 3, anything, every time you will run this code, it will be a bit different. There will be some randomness with it. So for predictability, I have set it to 0. Again, so now I'm going to apply k-means clustering to it. For k-means clustering, like I said, I have defined n4 clusters. Because I can see this data, I've said that I can roughly see four clusters. So I've said n is equal to 4. It will try to find four clusters in this data set using the algorithm that I have just described. And then I've set the model. It is really simple. It's just one or two lines of code. And then I will just see what it has the plotted. So if we see the visualization of how it ran the fitted module, it was basically able to define the four clusters like this. Like the blue point, the blue cluster here, the yellow cluster here, the maroon cluster here, and the green cluster here. All of this it did using the same algorithm as I described. You can even see the center points of the purple one here, and the yellow one here, and the blue one here. So you can understand over athlete that mostly it classifies data where classification does not exist. This is mostly a first step that helps people in researching customer behavior on in any data. You can see that overview that this is how most of the data is clustered. It is not exactly right, and you can't even check if it is 100% right or not, because if you try running any accuracy models on this, accuracy meaning absolute error, they will all give you values that just do not make sense, which is again predictable because we don't have any labeled data. This was all dummy data that I created, and it was unlabeled. So running any accuracy models on an unsupervised model is just not recommended, because it's not its job to do that. Its job is to just show you. It's just to classify data. Yeah. Again, so if we go back to the presentation, what are the drawbacks of using k-means? K-means is really sensitive to the initial choice of clusters. As you can see, even in this data, I can see four clusters, and I ran k is equal to 4. So it gave me four clusters here. If I had no idea how many clusters there were in a data, and it is really possible because I was able to graph this out here. Most of the times you won't be able to graph your data. So you won't be able to see how many clusters there are. So if you give a wrong number of clusters, or a too high number of a cluster or a too low number of a cluster, your final result will definitely vary, and it may classify something as something that it is not. So this is one of the things to keep in mind. Change is sensitive to outlets. FSU always looks for the shortest distance between points. Again, I saw another data that I created, but basically it's something, let's say there was a point right over here. It wouldn't have been classified, or it would have been classified wrongly because of its outlier nature. It was nowhere near the cluster. So in even those cases, you have to be really careful that your data set either you have cleaned all the outliers, or if your data set has outliers, it will definitely affect the way it has classified every other point on the data set. Again, the last one is again is the prior knowledge you may know need to know about the number of clusters. What I similarly to what I talked about in point one, you might not always know the number of points that you have, number of clusters you might have in a data. Now the last point is when you should use k-means clustering. So k-means clustering is used when you have a well-defined and separated when you have well-defined and separated clusters with no overlapping users. Again, it's a really good scenario for gaming clustering, as we saw here. All of the clusters were separated and they didn't have much overlap. But what if they had overlap? What if there was like they were not so nicely separated, like you can see them here? What will you do in that scenario? So for that, I even created a data set here. You can see this extreme case data set that it's basically not recommended to use gaming centers. It's not really clearly separated. And if you try running K-means on it, you don't even know how many clusters there are in this. I tried running K-means on it just for the sake of this example, and it was able to cluster something like this. Again, not the most ideal case, even for K-means. But if you do run it, this is what it will try to give you. Okay, and last thing, when you should know that when you should use k-means clustering is to when the computational efficiency of the algorithm is critical. For the right data set, k-means is really, really fast. Again, the algorithm I showed you how it worked was only 4 steps, basically 2 steps repeating one after the other. And they are really fast. If your data is clean and it is basically really fast to classify data using k-means, especially if you have lots of data and the points are, it's really easy to calculate the distances between two points. Yeah, I will try to sort everything here. I will try to end my presentation here because it's 6:30 now and I think everyone has other things to do. But yeah, my further explorations would be for this topic would be you can check out this YouTube video that tells the deep map, the time change clustering. It also this article that there's a deep dive into K-means algorithm with examples, and you can always try Kaggle with a lot of data sets and examples on K-means algorithm. So yeah, thanks. Handing it over to Fazwan now.
Yeah, Kash, thank you so much for the great presentation. So, as we come to an end of the event, I first of all thank to all the speakers that have spoken today and have discussed the different algorithms. So, today we have covered different algorithms such as regression, then you have algorithms and supervised learnings, algorithms which finds patterns, and it was a great session. So, I hope you guys enjoyed the session and I would invite you to join the session that is going to be next. That is about the deep learning fundamentals. And stay tuned for that session. And the links will be provided. And inform your friends to join the session. Thank you so much for joining.